Okay, so thanks for joining us, Matt. So we're going to start with the questions. So your line of work, which department are you working in?
Physics.
Physics, and which region of physics?
Atomic and molecular physics.
Okay, so within your research, is there any interpretation you believe works best, or is there any that you advise to follow?
So in my research we use gases of atoms and molecules, and more recently solid state systems, to try and engineer quantum states from the ground up by making them interact. And so in our approach we're not very concerned, although the long-term goal is to see whether we can make systems that are classically large, so macroscopic, that exhibit quantum features like entanglement and things. Our systems are very, very far from the classical limit. So many of the interpretational questions that get asked deal with the complexities of measurement and with quantum systems as they approach classical size, so things like Schrodinger's cat and so forth. In our case, we might be making measurements on individual atoms, individual photons, and so on. And here, the Copenhagen interpretation provides a very, very straightforward way of interpreting and calculating the results of experiments. We have to generalize it to some extent because an important element of this research is decoherence. So you can view decoherence as an unwanted measurement. So you're trying to keep your quantum information inside your system, but its coupling to the environment gradually measures, in some sense, the information in the system. And this means that you don't get the quantum dynamics that you hope for, but instead you start to see noise, which is essentially classical properties. So we do have to worry when we do the theory about how to deal with this decohering coupling to the environment.
Excellent. Okay. So outside of the research, where you're less likely to think about the implications of the physics, of the interpretations onto the physics, do you have any strong opinions on?
So actually, interestingly, a place where you really encounter this question is in teaching. So I teach a quantum optics course at level 4, and I begin with a purely wave function based approach to quantum optics, which is basically completely Copenhagen interpretation. We don't discuss any interpretational questions. But at the end, as we approach the research frontier, we have to deal with more thorny topics such as entanglement, and ultimately deal with this property of decoherence, where you have to invoke a divide between the system and the environment. And this fundamentally is the difficulty with the Copenhagen interpretation, that the measurement device is somehow viewed as classical and not part of your quantum description of reality, and your system is quantum and is described by quantum mechanics. And what vexes people most, I think, about the Copenhagen interpretation is that you're forced to put this line somewhere. So in the course I have to address the question of where do you put this line? How do you calculate things in practice? And at the same time, one must also consider, whether that theory has any kind of sensible meaning or is just a philosophical tool to do the calculations.
Okay. Okay, so let's look at that now. When looking at a quantum experiment, so a thought experiment like Schrodinger's cat or a real experiment like the double slit, how would you be inclined to interpret such observations?
So my own view is what I was taught in France, I would call the theory of decoherence, which is kind of the idea that a classical measurement outcome. So if you start with a spin, for example, which can be either up or down, it's a quantum system, but when you measure it, you get a pointer on some device that points up or down. How does the classical state of a pointer pointing up or down emerge from the quantum state? And the theory of decoherence provides an answer. It says, well, what happens when you make a measurement is there's some kind of entanglement between the system and the measuring device. And because the measurement device has many, many thousands more states than the system, then the classical effect, which is entropy, so the classical irreversibility that we have from entropy, a cup that falls on the floor is very unlikely, breaks into pieces, is very unlikely to come back again. It's very unlikely that the the evolution of the information from the system into the environment is going to reverse. And so this leads to a decoherence of the quantum system, and a classical measurement result that appears on some kind of device. And this, the question that leaves unanswered is, well, why that particular outcome? Because for a spin, 50% of the time I would measure up, 50% of the time I would measure down. It doesn't tell me why in one single realization I get up and why in another realization I get down. So it doesn't tell you where the randomness comes from. It just pushes the question down and says, well, it's just the same randomness that we have in classical mechanics.
Okay. A little bit on the consistent histories interpretation. It's quite a niche, small range accepts it. So do you know of any of its conventions, and do you disagree or agree with any of its?
So I wasn't aware of the consistent histories interpretation until you interviewed me, but having had a quick look at it, it's essentially very closely related. I think it's a more mathematically rigorous formulation of this theory of decoherence. And in particular, it appears that it also doesn't tell you which history will occur, but merely tells you certain rules for which measurement outcomes may occur and their probabilities in a more sensible and consistent way than the Copenhagen interpretation. So if you contrast it, for example, with the many worlds interpretation, so the many worlds interpretation gets around the randomness problem by saying that all measurement outcomes happen, but in different universes. And it seems to me that consistent histories approach still requires there to be some fundamental randomness somewhere. And the debate then is, what's the origin of this randomness?
Okay. And final question. So, with the interpretations of quantum mechanics, do you feel it's necessary to have a single interpretation rather than it be quite an open-ended topic? And is it really necessary for it to for work to continue to carry on?
I think what we know is that our theory of the universe is incomplete. Or at least, maybe it isn't incomplete, maybe this is as far as the story goes. But I think most people would hope eventually that the fact that we can't reconcile quantum mechanics and general relativity in any sensible way is clearly an outstanding and serious problem. And we're getting closer and closer to experiments where this problem is an issue, both in astronomy and cosmology, but also in things like detection of gravitational waves and so on and so forth. In the absence of that general understanding of space and time and quantum mechanics, it seems to me that it would be a bit irresponsible to suggest that we can shut off the debate over interpretation of quantum mechanics, because we don't have what we clearly have is some sense an incomplete description of reality. And so I think it is important to have these interpretive debates. I think for me the fundamental question is whether you believe that there is inherent randomness in the universe, whether that is classical or quantum randomness. So in Newtonian mechanics we have this belief that it's not random, it's deterministic. But we know from classical systems that undergo chaotic evolution, for example, that it's almost impossible to predict the outcome. And the reason is simply that there are so many possible states that the system can adopt. We simply don't have the resolution to measure what state it is in with enough accuracy to track that going forwards. And so in some sense it's a myth to me that the classical system is deterministic. If we think of classical gas in a box, we write down statistical properties of it, but we accept that at any one time there could be 10 to the 23 different sets of positions and velocities for those atoms in the box. And for me, you can argue that the quantum problem with not knowing the measurement outcome is not really all that different. There is some probability. Is this an inherent randomness, or is it just this randomness that arises because quite simply we can't know at any one time the state of the system well enough to make a deterministic prediction? And so I guess that's my view on that.